All right, Calc 3, welcome in. It's Tuesday, October 19th, and it's the start of week 10. Welcome in. We are currently in the section 13.5, talking about the chain rule. Now, we're done with the chain rule part, but there's a part at the end of 13.5 that starts to talk about how the chain rule for multiple variable functions can help us with implicit differentiation. So I want to start there. And this is a technique that you could have technically learned in Calc 1, but we didn't really have access to partial derivatives. And I'm always reminded when I used to teach at NIU, they actually, after teaching regular derivatives, they went over to the partial derivatives section right away in Calc 1 and taught that, and then came back and then did the implicit differentiation this way. I don't know if I agree with that 100%, but it is a topic that is going to is a topic that you could do in Calc 1 if you so wanted to. Just you'd have to talk a little bit about partial derivatives. But how does this get applied, right? So let's see here. Let's get an example of what I'm talking about. You might remember from Calc 1 you did something like implicit differentiation. So you wanted to say, let's say you wanted to do something like 2y squared minus 3xy plus x squared minus 5, right? And that equals 0, right? So you had some sort of mix and matching here, right? And you would end up doing what we called implicitly differentiate, right? Implicit differentiation. Okay. Now, just to remind ourselves of that, how we would approach that in Calc 1, right? We would take the derivative of both sides. Now, remember the setup here. X is an independent variable, right? Independent variable. And y is some function of x. We just don't know what that is, right? So y is a dependent variable, and it depends on x, right? And so in Calc 1, when we approach this, we would always take derivatives. The chain rule would apply, right, in Calc 1 when we had y squared. You're thinking of that as a function squared. And so, for instance, if I wanted to differentiate both sides of this with x, what I would get here would be 4y, but then times the derivative of the inside function. Well, the inside function is y, so this is times the derivative of y. So you'd say dy dx, or y prime, whatever notation you wanted. Right? And that would take care of that derivative. And then we would have to do this. Now, this would actually be a product rule here. I'd say negative 3 times the derivative of x times y. So the derivative of x, so keep x, times the derivative of y, plus keep y times the derivative of x, which is 1. Then plus the derivative of x squared, which is 2x. And then the derivative of negative 5, which is 0. And that equals the derivative of 0, which is 0, right? Maybe this is ringing some bells for you from Calc 1. This is the way that we would end up doing this. And now the next goal would be to solve for dy dx, right? So this would require a little bit of multiplication out, and then solving and getting dy dx stuff on one side and throwing the other stuff on the other side. So let's see if we can do that. We have 4y dy dx. Here we have negative 3x dy dx minus 3y plus 2x equals 0. I'm going to throw these terms over here to the right and factor out the dy dx, right? So I can do that, factor out the dy dx here, and I get 4y minus 3x equals, and then this gets over here. This goes 3y minus 2x. Yeah. Then I can divide by 4y minus 3x and now get an expression for the derivative for dy dx. So I end up getting that the derivative of the function y is going to be 3y minus 2x divided by 4y minus 3x, right? Something like that. And I mean, that was a process, right? And we called that process implicit differentiation. Yeah. So you may or may not remember that from Calc 1, but that's what we ended up doing there. Now, I'd like to show you, though, now that you know a little bit about partial differentiation, I would like to point your attention to a couple things here. Think about this function as a function of two variables. Instead of thinking of it as x as a variable and then y being a dependent variable, x, think of this for the moment as a function of two variables, x and y. Okay? And let's call that capital F. So in other words, I'm going to view this in a different light. In Calc 1, we viewed this as x is an independent variable and y depends on x. But in Calc 3, I could say, oh, I could also think of this as a function of two independent variables, y and x, yeah? Where this is 2y squared minus 3xy plus x squared minus 5, right? And now I want to point out here, what if I took the partial derivative of this function with respect to x? Well, you notice that this is 0. This would end up being negative 3y. This would end up being 2x. And the derivative of negative 5 is 0. Right? And what if I took the partial with respect to y? If I took the partial with respect to y, I would get 4y minus 3x. X squared derivative of that with respect to y is 0. And minus 5 derivative is 0. And I want you to take a look at what dy dx happens to be. A whole lot of matching going on here. Do you see this? We have 3y minus 2x. This looks like the opposite. We have negative 3y plus 2x. But this is totally this thing except the opposite of it, right? It's off by a minus. Fy, on the other hand, is exactly the denominator. So what we're going to learn here, and I can show this and demonstrate this using the chain rule in general, is the following. In this case, dy dx is going to be the formula minus fx divided by fy. And that's a whole heck of a lot faster to calculate usually. You see that? And so this gives us now an alternative way of doing implicit differentiation. We can now use our Calc 3 skills and come up with this equation now to do this implicit differentiation a bit faster, right? And not having to do like the implicit differentiation here and then the simplifying and then the saving. You wish you learned that one in Calc 1. I agree. Yeah. And so, you know, there are some folks that at NIU, that's what was their reasoning, right? They were like, it's worth it to say once you've learned derivatives, then learn partial derivatives, right? Just how to, you know, treat all the other as constants and just differentiate with respect to your variable, and then teach implicit differentiation. And so that way, then it ends up just being this little formula. Yeah. So it's kind of a nice way to think about it. Now, educationally, you do need to have technically a chain rule idea, and that's a little bit tougher to squeeze in there, right? For Calc 1. But hey, there it is. Now that you do know it, you can obviously apply it, right? So let's see why this works. I'm going to talk a little bit about why this is this formula here. So let's talk about the general scenario. All right. So suppose I have, right? Let's say that I have this scenario here. I have a function of two variables, just like I did in the previous problem. And let's say that it equals 0. Okay, so we know that to be true. All right. That's the setup, right? Because that's exactly the setup we had. We had stuff with x and y, and that equals 0. And so that was the setup that we had last time, right? Now, if I think of this as a function, right, what I can do here is let's call this w. Let's call this this capital F as a w, so, and make a little tree diagram like we did at the end of the video last time. So we have w at the top of the chart. W is a function of x and y, right? And because we're still in the same scenario that x is an independent variable, we do know that y depends on x. So it looks a little lopsided, right? But we do have this tree diagram, right? We have w going to x there and w going to y, but ultimately ending in x. You see that? And so we do have a chain rule. I could talk about what is the derivative of w with respect to the ultimate final variable, which is x. Do you see that? And so using this sort of chain rule, I can write this. The derivative of w with respect to x is going to be the following. The chain rule that goes along with this situation. This is going to be the partial of w with respect to x. Okay. Add that to the partial of w with respect to y times the derivative of y with respect to x. See that? That's what the chain rule would get us, right? Now, I know a couple of these things already. For instance, what is the derivative of w with respect to x? Well, the way that I've set it up, w is just the function 0. So, of course, the derivative of 0 is also 0. So we know that this is actually equal to 0. And the partial of w with respect to x, well, that's just capital Fx, the partial derivative of f with respect to x. Okay. Plus, here is w with respect to y. Well, that's capital F with respect to y. Times dy dx. Now remember, dy dx is the goal. That's what we want to solve for. We want to solve for dy dx because in implicit differentiation, I want to know what the derivative of y is with respect to x. But do you see now all I have to do is just solve this, which means I'm going to do what? I'm going to have to subtract fx off, right? And then to get dy dx by itself, I'm going to divide by fy. And that's where we get the formula. We get that dy dx is equal to negative fx divided by fy. And so that's why it works right there. It's just a matter of the multivariable chain rule that allows that to happen. Yeah. And so now we have that very nice way of working with it, right? And so, for example, if I have the following and I wanted to do this implicit differentiation, let's say I have y cubed plus y squared minus 5y minus x squared plus 4 equals 0. And I want to implicitly differentiate this and get dy dx implicitly. Well, I can now do it a real quick way. I can just say, okay, think of this left-hand side, it equals 0. Think of this left-hand side as capital F. Take the partial with respect to x. So that's gone, that's gone, that's gone. This is negative 2x. Take the partial with respect to y. So I get 3y squared plus 2y minus 5. Gone and gone. And now, just like that, we get that dy dx equals negative minus 2x, so plus 2x, over fy, which is 3y squared plus 2y minus 5. Yeah, maybe we did want that in Calc 1. That's nice. That's real easy, isn't it? All right, so there we have it. That is one little nice thing that you can do with that. Now, you can also apply this for higher level stuff. You can, there's formulas for the, let me get this situated here. We are not in statistics. This is the wrong textbook. Hold on. Let's open up the right one. There we go. And so we just did this. Let's see. Yeah, and so here are the other rules that you can have. You can implicitly differentiate with 3 variables, right? So here's how that looks like. If you have a function of 3 variables, x, y, and z, and you get them all on one side and it equals 0, what you can do then is ask for what's the partial of z with respect to x. It's that formula. What's the partial of z with respect to y? And it's that formula, right? I'm not going to focus too much on that, but those formulas do exist and they are out there. But I did want to connect you to the Calc 1 version that you did here. And so we have a Calc 1 version of implicit differentiation, and then higher order does this way as well. And then the formulas also, as you increase in order, these figure out in the way that you would expect them to very naturally. Yeah. But anyway, so that's a thing that exists. There it is. All right, we are ready now to move on to the next section, unless there's any questions with that. Hopefully we're doing good with that. What if we wanted to find the second derivative? Yeah. So once you have, that's a good question here. Once you have the first derivative here, then I don't really have many more tricks for you, right? So what I'm going to have to do is now just take the derivative of this again. You see that? And so I would have to take the derivative of this implicitly like that. Maybe then I could think of it as maybe then I could think of it as implicit differentiation and apply the shortcut in that way. But it doesn't end up coming up that way. I think all we would have to do is just take the derivative of this again implicitly like that. Right? That's all you would have to do there. And I don't think there would be a shortcut in that way. But you got me thinking about it now. Let me see. You got me also thinking that maybe they mentioned something in the homework about this. Hold on. Let me look at this real quick. Oh yeah, no worries. I'm glad you asked. I know there exists a formula for the second derivative because bottom line, you can just take another derivative, right? So you would just implicitly differentiate this. This book does not have a formula for the second derivative, but I'm sure one exists, and I don't necessarily want to spend time looking at that, trying to find it, but I think one does exist through that chain rule. Yeah. So anyway, let's move on to then 13.6. Okay. So 13.6 is a fundamental section, right? Talking about one of the most useful, or used, I should say, tools in multivariable calculus, right? And we're going to talk about the directional derivative and then invent something called the gradient. Okay? The gradient, yeah? Okay, so these concepts are related. That's why they're together here, but let's attack them separately a little bit here, right? I've been hinting at this all along, like when you're standing on a hill, on some sort of surface, right? And you look around, we already know that the slope in the x direction is the partial derivative of that function with respect to x, right? And then we talked about, well, if I look in the y direction, what's the slope of this surface in the y direction? And we've talked about that could be different, right? So like, for instance, that could be this here and then this sort of slope in this way, right? And so those could be different slopes depending on where you're looking. And the x derivative, the partial derivative with respect to x, and the partial derivative with respect to y can be different, but they are the slopes in those directions. So the natural question arises, can I pick any direction that I like? Do I have to pick the x direction? Do I have to pick the y direction? What if I wanted to pick like the 45-degree angle, right? And go off in that angle way instead of going in the x direction or the y direction? What if I went 45 degrees from the x direction? Is that possible to figure that out? And of course, I wouldn't be asking unless the answer is yes, yeah? And so that is the idea of the directional derivative. So the setup to this is going to be the following. I'm going to be given a direction that I care about, right? North, south, east, west, but it's going to be given in a unit vector way, direction. And the goal will be to tell you what the slope of the surface is when I walk in that direction. Right? So it's literally the job of fx and fy, except now instead of just being relegated or restricted to the x or y direction, I am available to do any direction 360 degrees, right? That's what I want to set up. So to get that going, let's take a look at these pictures. I was going to make something in GeoGebra, but I couldn't. I keep meaning to do something really neat for this section, but I keep not doing that, right? So I have to use these pictures in the textbook. I know. Gasp. They don't even move. I mean, what? What is this? This is a static picture? What are you talking about? So anyway, here we have this surface right here, yeah? And let's say that I'm looking in the direction that's given to me by a unit vector called u, right here, right? And so you're standing on the surface somewhere, right? And you're looking in that direction. It's not in the x direction, it's not in the y direction fully, right? It's in the u direction, yeah? And so what I want to do is think about a plane that cuts this very much at that angle. Do you see that? And that intersection creates a curve, just like this, right? And what I'd like to do now is say, well, what is the slope of that curve at this point? Yeah. And so I'm literally asking, what is the slope in this direction, right? To set that up requires a little bit of, some work here. So let's see what we got. They start off with saying, let's have a surface, z equals f of xy, right? And we have a certain point that we care about. So the point is at x naught, y naught. Yeah? And we're given a unit direction that we want the derivative in, right? So that we want to find the slope in this direction. Remember, we can state any unit vector in terms of this parameterization of cosine theta I plus sine theta j. Yeah? And theta, again, is the angle that it makes with the positive x-axis. All right? So that's our setup, right? Now, they start to work on this a little bit, and they say, okay, well, we want to come up with that intersection of a line, and they go ahead and they work on that, and they get this here, this parametric equations of that line, and then they start to equate some things here, right? The distance between P and Q, and they go ahead and get that, and they write the slope, and lo and behold, when they do all of that, this is the definition that we want to work with. Basically, look at this. We're sitting at x naught, and they bump a little bit in the direction of the I component of the u vector that they gave me. So this is some parameter times cosine theta. So that's like nudging x in the direction of u a little bit. And they take wherever your y naught is, and they nudge it a little bit in the direction of t sine theta. Right? They take that difference, divide it by t, and we have that idea of a derivative that you've seen time and time again. It's like a limit as t goes to 0 of, the difference quotient here, right? Now I'm going quickly through this because we're not actually going to be using the definition for calculation here, right? But that is our set derivative, right? A couple things I want you to get out of this is a limit of a fraction, right? And so as such, the directional derivative is a number if that limit exists. So the directional derivative is a scalar. It's a quantity. It's talking about the slope in a certain direction, right? Now, one thing that we're going to take real good use of here, and this is where you want to start writing things down in this thing, is how can we calculate this? And there's this really cool connection between the directional derivative and the partials that we already know how to calculate. And it ends up being this formula right here. So this is what I'm going to write down on paper. And look at this, the proof of this. Do you see buried in here? Apply the chain rule. So thank you very much, chain rule, because the chain rule is true. It allows us to go from this sort of parameterized line that they worked on here to get a nice format for this and to get this in terms of partials. So for our purposes, we will take advantage of that, not think too hard about the directional derivative definition, because our purpose here is calculation for now, right? So here we go. The directional derivative is going to be the following. The notation's a little crazy. So capital D for derivative, they do a sub u, right? So this is like the directional derivative in the direction of u of the surface f of xy. And so that's a whole lot of symbols in this notation, but that is the notation that we use. All right, so directional derivative of f of xy in the direction of u is going to equal the partial derivative of f with respect to x at xy times the cosine of theta. Remember, theta is the angle that the unit vector u makes with the positive x-axis, plus fy xy sine of theta, okay, where u equals cosine theta I plus sine theta j. Okay. Now, technically, we don't count this as the definition, but I'm going to basically treat it as if this was the definition of our directional derivative, right? Awesome. So we have this very nice thing that we can just calculate, right? So you tell me the direction that you want. I'll have to parameterize it in terms of its cosine sine pair. And then I will have to just calculate the partials of the surface that I'm working with. And now I have an understanding of how the slopes work no matter what direction I'm looking at. 360 degrees view from where I'm standing on my surface, right? So let's go ahead and just do a problem here. All right, so here's my surface, f of xy equals 4 minus x squared minus 1/4 y squared. Okay. And we are interested in the slope of this, the directional derivative. Find directional derivative. Okay. At the point 1, 2. So that's the x value and the y value that I care about. In the direction of 60 degrees from the positive x-axis. Okay. Okay, let's go ahead, and before I even do anything here, let's just get our bearings on this problem by looking at GeoGebra real quick, looking at the surface that we're working with. All right, and so let's go ahead and type that in here. Oh, I lost my input. Hold on. Input bar, come back. Oh, and I lost my axes and my grid. What? GeoGebra. GeoGebra has been giving me issues lately. I don't know why. Maybe I need to reinstall it. Okay, so we got that. Let's see. Oops. I'm having issues here. Hold on. Okay, I just needed to reset. Now, can I do new? All right, new. There we go. Wow. Okay. Yeah, I wasn't liking any of that. So now I think I've reset it. Here we go. So 4 minus x squared minus 1/4 y squared. All right, cool. So that's my surface right there. Okay. And remember, the red axis is the x-axis. The green axis is going to the right. It's the y-axis. And the z-axis is the blue axis, pointing straight up. Now, we care about the point at above 1, 2. So I'm going to plot that point. So I'm saying 1, 2, comma, the function at 1, 2. Okay. So this is where I'm standing on this surface right there. See that? Okay, I'm standing right there. And now I'm interested in walking 60 degrees from the x-axis. So you can see that that would be somewhere like, so yeah, that would be, here's 0 degrees, right? This would be parallel with the x-axis right here. So I want to move 60 degrees from that. So like above view, right, would be 60 degrees would be something like this. So I want to walk off in this way, right? 60 degrees like that. Yeah. And the question is, what is the slope of the surface when I walk off in the 60-degree direction? Okay. That's what the question is. What is the slope in that direction? All right. Now, to get to that, let's go ahead and work this out on paper here. So first things first, our formula for the directional derivative is fx times cosine of theta plus fy times sine of theta. Okay? So I need to first get my unit direction vector, right? Now, this does have to be unit length. If it's not unit length, you will be getting the incorrect amount. It's the wrong scaling, right? And so this formula is depending on that this is a unit length vector here. So I am talking about cosine of 60 degrees here, I, plus sine of 60 degrees, j. That is the unit vector that we're working with, right? Now I need my partials. So let's go ahead and get those. Fx is negative 2x. Fy is negative 1/2 y. Okay, like that. And so now my directional derivative in general for any xy is the following formula. It's going to be fx, which is negative 2x, times the cosine of theta. Now, theta is 60 degrees, or pi over 3, right? Plus Fy is negative 1/2 y times the sine of pi over 3. Okay. Now all I have to do is to find the directional derivative at the point that I care about. The x-coordinate is 1. The y-coordinate is 2. And so now the directional derivative at 1, 2 is going to be negative 2 times 1 times the cosine of pi over 3 minus 1/2 times 2 times the sine of pi over 3. Okay, so all we have to do is now calculate those, and we are on our way. Yeah. So here we go. The cosine of pi over 3 is going to be 1/2. Right? And negative 1/2 times 2 is 1. Sine of pi over 3 is root 3 over 2. So we end up getting negative 1, that's 2 times 1/2, minus square root of 3 over 2. And from that picture, I could tell it was going to be a negative slope, right? It was going downhill, wasn't it? When I was moving in the 60-degree way, right? In the direction there. Typing that into your calculator, you get this is approximately negative 1.866, right? And so this would be a slope of, what would this be? Rise over run in that direction, right? So this would be z units divided by the xy units, right? Whatever would be in the xy units, yeah? And so this is how many, height units in terms of units going across, right? Like that. And so that would be the slope of the surface, right? And you can see that this depends on where you're at, right? It depends on where you're at because x and y are still involved in the formula. And it, of course, matters what direction you're looking in. So these are all the things that go into wondering what the slope is in a certain direction, right? It matters where you're at. It matters what direction you're going. And this is exactly how it matters, right? It goes into that calculation. All right, awesome. Let's do another example. So new function, let's do x squared sine of 2y. We care about the point 1 comma pi over 2 in the direction of 3i minus 4j. Okay. So we have all of our pieces here. We have the surface described, we have the point at which we care about, and then we have a direction to go in. Right? So now I'm thinking about, okay, let's think about my formula, the directional derivative formula. I need the partials. I need cosine of theta and sine of theta. In other words, I need a unit vector, and I need to know its I component, because its I component is going to be cosine of theta, and I need to know its j component, which is sine of theta. I can do this in this problem without knowing theta, right? Because it's whatever number that sits here and here, that's going to be the I and the j. I do have to make sure, though, that it's unit length, okay? And I don't think this vector is, right? So let's call this vector v. And what I want is u to be a unit vector in the direction of v. Right? So I'm going to take v and divide by its magnitude. Right, now its magnitude is what? This is going to be 1 over square root of 3 squared plus 4 squared. Right, so that's 16 plus 9 is 25 times 3i minus 4j. Of course, the square root of 25 is 5. And so I end up getting 3/5 I minus 4/5 j. That is the unit vector that I care about. Now, do you see that I don't need to actually know what theta is here, right? This is already, whatever sits here is already cosine theta. And whatever sits here is sine theta already. And so without me knowing what theta is, I can still figure out what cosine of theta and sine of theta are. Okay, with that out of the way, let's go ahead and get our directional derivative. So we want the directional derivative for the surface F. I need partials. So the partial derivative with this respect to x is 2x sine of 2y times cosine of theta. What's cosine of theta? 3/5. Add to that the partial derivative of this with respect to y. So that's going to be the derivative of sine of stuff. So that's going to be cosine of 2y times 2 times the x squared out in front, like that. Okay. And then that's going to be multiplied by sine of theta. What's sine of theta? Negative 4/5. Please remember, the directional derivative is not a vector. Notice there's no I and j component here, right? It's actually a scalar, right? Okay, so let me simplify this a little bit. What do we have going on here? Let's see. We can have 6/5. Now, let me plug in values here as I go as well. So I want this at 1 comma pi over 2. So x gets replaced with 1. Sine of 2 times pi over 2 is pi. Oh, that's nice. Sine of pi is 0. So that's going to wipe out. I think I took care of everything there, though. Plus 2 times 1 squared times cosine of pi times negative 4/5. Sine of pi is 0. That's gone. Here we get 2. Cosine of pi is negative 1. So that's going to be negative 2 times negative 4/5, which ends up being 8/5. Okay. So if I was to plot this surface, look at this point, look in this direction, it would look like I'm increasing height. The slope is positive, and it's 8/5. So 8/5 rise units over run units. Right? Awesome. Any questions with the directional derivative? Because now I'm going to move on to a related concept. And I'm excited about this because I've finally gotten to the point where we can talk about the object, the mathematical object, that is really the closest thing we'll ever get to saying this is the derivative of this multivariable function, right? Because it does the things that we like derivatives to do, right? The gradient does that, yeah? And so let's go ahead and I'm going to define what the gradient is and then show you it behaves and does the same sort of applications that we expected the derivative to do in Calc 1, right? And so this is finally an answer to the type of object that we were expecting to say, hey, this thing is doing things like derivatives should do. Now it happens to be a vector. It happens to be a vector that does that. But nonetheless, it behaves like a derivative in many, many scenarios. Yeah. And so we end up defining something called the gradient of a function. The gradient of a function. Okay. And for now, we're going to stick to 2 variables, but we'll easily see that this expands to 3, 4, 5, 700 variables. Yeah. Gradient of a function of 2 variables. And the definition is the following. We get a symbol here. We can either say grad f. That is sometimes used. We'd say grad f. We also have this notation, which is read del f. This is del f. Okay. Those are nice notations. That doesn't tell me what it is, though. Here we go. Here's what it is. It's the partial of f with respect to x times the I component plus the partial derivative with respect to y times the j component. So notice that if I have a 2-variable function, right, a function with 2 variables, the gradient is a 2-dimensional vector whose components are the partials of that function. And since it's a 2-variable function, we have 2 partials. And notice that the partial with respect to x is associated with the I, and the partial with respect to y is associated with the j. But the gradient of a function is a vector. The directional derivative of a function is a scalar. The gradient of a function is a vector. You see that? Now, one thing we want to make note right away, please notice that this is a two-dimensional vector. So your book reminds us that this is a vector in the plane. Vector in a plane, not 3D space, right? So I like to think of it this way. And once we start getting into what the gradient does and what it looks like, I like to think of it as like standing at the point on a hill. I'm holding a compass, right? But I'm holding it flat, right? So the arrow, the needle of the compass is not allowed to go up or down like this. It's only allowed to spin around like this, and it's pointing in a certain direction, right? That's how I want you to think about the gradient here. So I am standing on a surface that looks like it's in a 3D space, but the gradient itself is like holding a compass that's only allowed to spin around in 2D space. It's not allowed to go up or down like that. Yeah. And so that's a nice visual to have while you're standing at that location, right? Okay. Now let's see here. Let's talk a little bit before we get into this a little bit, what this symbol means by itself, right? This del operator, right? We call it an operator. It's an operator in the same sense that ddx is an operator, right? And so that means that this is telling you an instruction. It's telling you do something, right? Do something to a following function, right? Just like in Calc 1, this meant take the derivative of this single variable function that follows, right? So do ddx of, and it's waiting for something to operate on, yeah? In the same sense, that's what del is. Del is waiting for a function to operate on, right? So we can say when del operates on fxy, it produces the vector del f, in other words, the gradient. Okay, so this symbol by itself means it's an operator, means that it's performing some operation on a thing, and I can just talk about the operation in and of itself, right? And not have the thing that it's actually performing that operation on, right? It would be like me saying, hey, that's the addition operator, right? So I can talk about addition just by itself. Yeah. Awesome. So let's do some easy introductory examples, and these are just very much, did you pay attention to the derivative, the definition of the gradient? Yeah. So let's do it. We're going to say, for example, find the gradient of the surface f of xy equaling y ln of x plus xy squared at the point 1, 2. Okay. So the gradient requires me to take partials of the surface, right? So I need fx and I need fy. Then I need to assemble them together in a vector, and that will be the gradient of f. Okay. So let's go ahead and do that. First things first, let's calculate the partial of f with respect to x. So I'm going to get y is a constant, ln of x, derivative of that is 1 over x. So this first term is y over x. Then we have the derivative of this. That's going to be ending up to be plus y squared. Okay. We have the partial of f with respect to y. So here the variable is y. So the derivative of this is going to be ln of x, right? Because like the derivative of 5y would just be 5. And so the derivative of ln x times y would just be ln x, right? Plus 2xy, right? Doing that. Okay. Now those are my partials. And so now I just have to assemble them and write up the gradient. Therefore, the gradient of f at xy is going to be the following thing. It's going to be y over x plus y squared I plus ln of x plus 2xy j. So that's my gradient at all xy values. Okay, they didn't ask for that. They asked for the, at this point, but I will ask you for this multiple times, right? So this is what I mean by the gradient at any xy, right? But now specifically, I want to find the gradient at 1, 2. So this is just as easy as plugging in 1 for x and 2 for y. So I'm going to end up getting 2 over 1 plus 2 squared I plus natural log of 1 plus 2 times 1 times 2 j. So doing this arithmetic gets me 2 plus 4, which is 6. So I get 6i. ln of 1 is 0. 2 times 2 is 4. So plus 4j. So the gradient when I'm standing at the point 1, 2 is 6i plus 4j. Remember what I was talking about? So imagine yourself standing at the point 1, 2 on the surface, right? So you're standing at some height, right? And you're holding a compass, and that compass is pointing in the 6i plus 4j direction. Okay, notice there's no k component, right? It's not going up or down, anything like that, right? We'll get to very soon what this vector means, what this means physically, what it looks like. But for now, let's just note that it's a two-dimensional vector, right? Even though I'm working with a three-dimensional surface, the gradient is a two-dimensional vector. So think of it as like holding a compass at a certain location. Are there any questions in chat on this? Any questions? Is anyone awake in chat? Sorta. Okay, that I'll take it. I'll take sorta. Maybe it's my soothing math voice. We can do math ASMR videos. Anybody interested in that? They'll probably go viral. All right, so now let's get into a little bit of what the gradient does, right? What are its properties? What can I calculate with it? What does it show up physically? What does it physically mean, maybe, if anything, right? The first thing I'm going to do, though, is connect it right away to the directional derivative. They are very much connected, right? And you say, how can that be? Because the directional derivative is a scalar, and the gradient is a vector. So there are two different worlds, if you will, right? But they are connected through a dot product. Let me show you something. Now let me rewrite the definition of the directional derivative, right, that we used. Right? We had the directional derivative was equal to fx times the cosine of theta plus fy times sine of theta. Now, thinking about this, this looks like a dot product if you think about it, right? Notice how it's like something times something plus something times something, right? Now, all that would have to match up are these components, right? So check this out. If I think of this as fxi plus fyj and dot that vector with cosine theta I plus sine theta j, do you see how that's the dot product, isn't it, right? So it's this times this plus this times that. But wait a minute, these vectors now have other names. We know what these are. This is the gradient right here. This is fxi plus fyj. So this is del f. And it's dotted with our our direction that we're pointing in, right, which we called u. And so we get this nice alternative form that connects the directional derivative with a gradient via a dot product. So the directional derivative of a surface is simply the dot product of the gradient with the direction you're looking in. See that? And that's kind of cool. That's clean. That's a real nice way of thinking about it, right? Obviously, it's sort of been defined to do this, but yeah, that's a nice connection, right? Remember that this is giving you slope information, right? So getting a slope information is tied to this vector that's like I'm holding a compass with a vector pointing in a certain direction. Yeah? And it involves the direction you're looking at. We can use this information to figure out various properties of the gradient. And once we see these properties of the gradient, you'll start to recognize, oh, that's exactly what we did in Calc 1 with the derivative, right, in certain cases, yeah? So let's take a look what we got. So we're going to say properties of the gradient vector. Okay? Remember in Calc 1, if I told you that the derivative was 0, right, at a location, that did mean that the slope of the tangent line, the slope at that point was 0, right? We get the similar idea here in multivariable. We get the first idea that says the following. If the gradient vector is the 0 vector, okay, so I can't say the gradient is 0, I have to say the gradient is the 0 vector, right? Then we can actually conclude something about the directional derivative. Remember, now the directional derivative tells you information about slope. The slope is 0 for all directions u that you look at, right? So in other words, if the gradient is the 0 vector, what I can conclude from this is that any direction you look at the point you're standing, any point you look, it's going to be a horizontal slope, right? So maybe you're at a peak. Could you see that? Being at a peak of a surface, you're standing at the peak and you look around and the slope of at the peak is 0 all the way around, right? You don't even have to be at a peak. You could be at a valley, right? At the bottom of a bowl, for instance, right? Looking around at that center point there, you would look around and technically it would be flat locally to you. Your directional derivative would be 0 no matter what direction you looked at. Now, as soon as you take a step off of that center, now your slopes have changed, yeah? But at that point, my directional derivative is 0. Why is this true? Well, if I'm allowed to start with this, right, it says if the gradient is 0. So I'm allowed to start knowing that the gradient is 0. But wait a minute, if the gradient is the 0 vector, I am now dotting 0 with any vector u. And 0 dotted with u is the scalar 0, which means this calculation is 0, which means that the directional derivative is 0. So a little tiny proof of this, right, would be that the gradient of f is 0 implies that gradient of f dotted with u equals 0 dotted with u, which equals scalar 0, which is, because this is the formula for the directional derivative, that means the directional derivative is 0. And notice that u did not play a role in this, right? This was, no matter what the components of u were, they're being multiplied by 0 and then added together. So u can literally be any unit vector it wants to be. So I get that this is the directional derivative value for all u. Okay, awesome. Now, the second property is recognizing this formula is a dot product, right? Which means that I can actually sort of recast this even more. All right. I'm going to pull some knowledge back from chapter, I think, 11. Yeah. Here we go. We know that the directional derivative equals del f dotted with u, right? But thinking about the dot product, remember the dot product had an alternative formula of the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Do you see that? So now, the magnitude of the gradient, I don't know what that is because that'll change depending on what the gradient is, right? But I certainly know the magnitude of u because in our context, has to be a unit vector. So I know this is equal to 1. So this tells me that the directional derivative is actually the magnitude of the gradient vector times the cosine of theta, where theta is the angle between the two vectors. And what are my two vectors? Between the gradient vector and u. Remember, u is the direction I'm looking in, and the gradient's pointing somewhere else. And so maybe it's like this, right? So, I'm pointing in this direction here. Maybe I'm looking in this direction, and the gradient is pointing in that direction, right? And so these form an angle between the two, right? We call that theta in this case. So that's going to be a nice formula because we're going to actually get some things about this. Notice from this that the directional derivative now it's bounded, right? There's a maximum and a minimum value that the directional derivative can be. Do you see that? This must be the case because the magnitude of the gradient is a finite number, right, for our purposes here. So that's a finite number. And then it's being multiplied by the cosine of theta. Now, cosine of theta, no matter what angle I make, is stuck between 1 and -1. So this means that the directional derivative, right, has only the maximum it could be is the gradient of this times 1, because that's the maximum cosine could be, right? And on the other hand, the smallest value or the least value that this could be is if cosine was its minimum, -1. So the minimum that the directional derivative could be is the negative of the magnitude of the gradient. So do you see these two ideas are tied together? The directional derivative cannot just be whatever it wants to be. It's bound by what the gradient dictates, right? It's bounded by the magnitude of the gradient times the cosine of the angle between it. And we know there's only a certain amount of cosine values that are possible. They're stuck between 1 and -1. So this leads to our next two properties of this. This exact idea gets us the following statement, and this answers the question, what's a physical interpretation of the gradient? Right? So property 3. The direction of maximum increase of a surface F is given by del F. And the maximum value of the directional derivative of F is equal to the magnitude of the gradient. This statement's very powerful. It tells me what the vector itself does, and it gives me meaning to the magnitude of the gradient. All right? So let's go ahead and go through this a little bit. So do my proof again. I sort of walked you through the proof in words, but now let's actually write it down this time. All right? So we know from property 2 that the directional derivative is actually equal to the magnitude of the gradient times cosine of the angle between them, right? So the maximum value that the directional derivative could ever be is magnitude of the gradient of f, right? Where the cosine of theta is 1. Right? But now, wait a second. If the cosine of theta is 1, what does that mean for my angle between u and the gradient? This tells me information about the angle between those two vectors, doesn't it? All right, so a little unit circle time. If my cosine is 1, that means my x-coordinate is 1. That means that the angle between the direction I'm looking at and the gradient vector is 0 degrees. In other words, I'm looking in the direction of the gradient. What that means is when I look in the direction of the gradient, the directional derivative is as big as it can get. So that proves the statement. The direction of maximum increase, the largest slope possible of f at a given point, is given by the gradient vector itself. So I'm standing there on the hill, standing at a point, looking at my compass, and my compass gradient is pointing in this direction. What that means is if I walk in that direction, it's going to be the steepest uphill that I have, right? And as I move around, the gradient vector changes its, where it's pointing, but at any location, it's pointing in the direction of maximum increase. So if I was to stop here and look at my surface, and I walked in that direction, that would be the highest uphill. Now notice the gradient's not pointing uphill. The gradient's just pointing in the compass direction of which I need to go to experience the direction of maximum increase, right? Okay, so let me finish this off. So where cosine theta equals 1, this implies that theta is 0 degrees, meaning u and gradient of f are parallel, right? Pointing in the same direction. And that's the argument why this is true. So let's summarize what we got. What does the gradient do? It points in the direction of maximum increase of my function. What does the magnitude of the gradient tell me? The magnitude of the gradient tells me what is that maximum slope. That tells me what the slope is, and that's the biggest slope possible at that point. Right? Nice. Okay, I can now say the exact mirror situation. I can say the following. I can say the direction of minimum increase of f, okay, is given by not the gradient, because I know the gradient points in the direction of maximum increase, but kind of nicely, this is negative gradient of f. In other words, the opposite direction, right? So if I look in one direction, it's the maximum increase. This says look to the opposite, and then that's the maximum decrease. Maximum decrease means minimum increase. Thanks, English. So here we go. And the minimum value of the directional derivative is negative magnitude of the gradient. Okay. And again, the proof of this, the idea why this is true, comes from the same exact formula, but now instead of thinking about maximum value, I'm thinking about minimum value. Right? So I start off again with this, and I say, okay, the directional derivative is the magnitude of the gradient of f times the cosine of the angle between them. If I want the minimum value, I want this to be the minimum value. This is got to be the most negative it could be. What is the most negative it could be? That would be negative magnitude of f, grad f, because cosine of theta would have to be -1, which is its minimum value. Right? So this is its minimum value when cosine theta is its minimum value. So where cosine of theta is -1. But now, wait a minute, what does that mean for my angle? If my cosine is -1, that means I'm over here, and now I have an angle of 180 degrees. Do you see that? So I'm pointing now, I'm looking in the opposite direction of the gradient. The angle between the direction I'm looking and the gradient is 180 degrees. I'm pointing in the opposite direction, or I'm looking in the opposite direction from my compass. So theta equals 180 degrees, meaning u and gradient f are pointing in opposite directions. Okay? Very good. All right, so I want to finish this video today by doing an example here that I'm using this a little bit here. So suppose I have a plate, a metal plate, right? And I have a function that measures the temperature on this plate, right? So suppose I have a temperature function. You tell me where you're located at on the plate, right? I can put an XY coordinate system here on it. And the temperature works like this: 20 minus 4x squared minus y squared. Okay. So this is the temperature in Celsius, right, on the surface of a metal plate. X and Y are measured in centimeters. Okay. So I have a question. In what direction from a certain point, from the point 2, -3, does the temperature increase most rapidly? Okay. So let's go ahead and think about what we're doing here. So I'm living on the plate here at 2, -3. So that means I'm on the plate right here. And I'm interested in what direction do I go to experience the greatest increase of temperature, right? So notice that, where I live depends on what the temperature is. And in fact, just look sort of casually at this. There's a maximum temperature, isn't there, right? At the origin, this is 20 minus a positive thing minus a positive thing. So the largest temperature that this plate could ever be is 20 degrees Celsius at the origin, right? Anywhere else is going to be smaller, right? Temperature, right? Temperature is going to be less, yeah? So the question is, what direction do I look at to experience the greatest rate of temperature increase? Okay. Now that seems like a difficult question, right? Except we just learned about the gradient and its property. The gradient points in the direction of maximum increase. So this is just a fancy way of asking, calculate the gradient of this surface, and then plug in the point that you're at. That is the compass, that is the direction that you must walk in to experience the greatest temperature increase, right? Now, some of you might be saying that, well, I know this is the hottest point on the surface right here at the origin, so I bet you it's going to point towards the origin, right? So the way that I would experience the highest rate of increase, temperature increase, would be to move towards the origin, right? What we're going to find out is that's actually not true. That's actually not true being at this spot. So let's see what we get. Let's end up what we're getting. So this would be the gradient, would be del T. Okay, so I'm going to calculate del t. And that's going to be the partial derivative with respect to x. So that's going to be negative 8xi. Then plus the partial with respect to y. So that's going to be negative 2yj. So that's the direction that I should go in. Now just plug in the point where what you care about. So what is the gradient vector at 2, negative 3? And so we get negative 8 times 2i minus 2 times negative 3j. So this means I get negative 16i plus 6j. Okay. So what this actually tells me here is that I should walk in this direction. So this is going to be off screen a little bit here, but I would have to go 16 units, right? 16 units here to go there like that, and then up 6 units, right? Let's me maybe, yeah, I mean, I could divide by a certain number here. Like if I divided by 4, right, that would be parallel to that. So if I divided this by 4, I would go negative 4 over 1, 2, 3, 4. And then, so 1, 2, 3, 4. And then up 6 divided by 4, which is 1.5. So 1.5. So basically, roughly speaking, I would have to walk in this direction. And even from my poorly drawn picture, you can see that that is not walking towards the origin, even though the origin is the hottest point on the plate. But that's not what it asked, right? It asked, in what direction does the temperature increase most rapidly at this location? And it ends up being this direction here, and that does not mean going towards the origin directly. Okay, so that's what we have here. Now, what is that rate of temperature increase in that direction? So now, what is that rate of increase? Okay. Well, again, this is really just asking from our property that we did on the previous page. This is literally just asking what is the magnitude of the gradient, right? Because the rate of maximum increase is just the magnitude of the gradient. So this is asking me for the magnitude of the gradient of t at 2, negative 3. In other words, what's the magnitude of this vector here? That's going to be the square root of negative 16 squared plus 6 squared. And so doing that, let's see. I don't know 16 squared off the top of my head. Probably should. 256 plus 36. Square root of 292. Square root of 292 is about 17.09. Right? Now let's think about units here, right? So the gradient, right, is measured here. This rate is measured in z units per xy units, right? Well, I'm measuring temperature. So that is in degrees Celsius. And the xy are measured in centimeters. So this means that this rate would be degrees per centimeter. Right? So if I was to walk in this way, this direction, I would be experiencing 17 degrees every centimeter, right? On average, in that way, right? Now, of course, as soon as you move off of this point, actually move off this point, the gradient has now changed directions, most likely, right? Because it depends on where you're at. X changes and Y changes, your gradient changes, right? And so what you will find is as soon as you move in that direction, right, it now points in a new direction, which means it might have to turn to get to where it's going, right? So next time I'm going to talk a little bit about this. If I had like a heat-seeking, not a missile, but a particle, a heat-seeking particle. The book is very clear that this is not a missile. It's a heat-seeking particle. Okay. And so what that means is I want to sort of keep track along the way. When you do move away here, calculate the gradient again, then go in that direction, right? And so then make this particle at every sort of instant in time always go in the direction of the steepest ascent, the maximum increase of temperature. I wonder where you would end up in the long run. In other words, would it seek out the origin, which we know is the hottest point on the plate, right? We'll figure that out next time for Thursday. All right. Hope you enjoyed today's video, talking a bit about gradients and directional derivatives. These are fundamental topics for multivariable calculus. It's our idea of derivative. Notice that when the gradient is zero, the slopes are zero, even in higher dimensional thinking right there. So we're going to be talking more and more about this in the days to come. And so hope you enjoyed that. All right. Until next time, everyone, looking forward to checking in with you on Thursday. Hope you're staying healthy and happy, and looking forward to next time. All right. Until then, be well. Bye now.